Welcome to Lecture 7 of the Information Theory course. I'm your instructor, PhD student at the Indian Institute of Science, Sachin. Today we'll be solving a few problems that make use of all the concepts that we learned in the previous 6 lectures. So this is the problem solving session, the first problem solving session on the basics of information theory. So I'll read out the question and only write down the relevant data. I won't write down the question. If you want the questions, you can refer to Elements of Information Theory by Thomas M. Cover and Joy A. Thomas, second edition. And these are problems from chapter 2 in that textbook. The first question is on coin flips. A fair coin is flipped until the first head occurs. Let capital X denote the number of flips required. Find the entropy h of capital X in bits. That's part A. Part B says a random variable x is drawn according to the above distribution. Find an efficient sequence of yes/no questions of the form is capital X contained in the set capital S. Compare h of capital X to the expected number of questions required to determine capital X. And they have given two mathematical formulas that might be useful in finding the exact value of the average number of questions and the entropy. So the question says a fair coin is flipped until the first head occurs. That's the experiment. The random variable x denotes the number of flips required to get ahead. And part A asks what is the entropy of h of x. So the possible values that the random variable x can take and the probability that the random variable x takes that particular value. I'll write that down in the form of a table. So capital X can take value 1, that is, you can get a head in your first coin toss, then capital X will be equal to 1. The probability of that happening is half because it's a fair coin. Capital X can take the value 2, that is, the first head appears on the second coin toss. So the sequence of head and tails is TH. The first toss must have been a tail. If the first toss was a head, that would come under this particular outcome. Then x value would be 1. So if x is 2, the first head occurs in the second toss, so all the previous tosses are tails. The probability of this happening is probability of the h, but the coin tosses are independent, so it's probability of t, probability of h times probability of h. But these are both equal to half, so it's half square. Similarly, the x can take the value 3, That means the first two tosses were tails and the third toss was a head. This occurs with probability half power 3. And so on. The probability that x takes the value n is half power n. So the first n minus 1 tosses are tails, and the nth toss is a head. But for this question, since it's a fair coin and the tosses are independent, that's what you are assuming, the probability is just half power n. Now the um, values that x can take belong to script x, where script x is a set of natural numbers noted by n, and the entropy of this random variable x is summation over all x in script x, probability of x log 1 over probability of x, which is summation over all natural numbers, probability that x takes the value 1 is half, x takes the value 2 is half square. So the probabilities are all powers of 2. So px of x is half power x log 1 over half power x, which is log 2 power x. So this is nothing, 1 over half power x is nothing but 2 power x, and log of that to base 2 is nothing but x, so it's x, and this is a geometric series. Sorry, this is not a geometric series, but the textbook gives you a formula to calculate the sum. So the hint is this: summation n is equal to 0 to infinity n r power n is r over 1 minus r whole square. This is also equal to summation n is equal to 1 to infinity n r power n, because when n is equal to 0, this is 0. Comparing our entropy formula to the given formula, we can see that r is equal to x, sorry, r is equal to half and n equals x. So we are using the variable x, and the formula uses the variable n, but it's the same summation. Therefore, h of x is r over 1 minus r whole square, which is half over half square, which is 2 bits. In general, instead of a fair coin, if we had a biased coin with the probability of heads being P and probability of tails being 1 minus P, let's call it Q, then h of x is summation over all natural numbers q power n minus 1 p. That's the probability that the first head occurs in the nth toss. So n minus 1 tosses, first n minus 1 tosses are tails, which happens with probability q power n minus 1, and the nth toss is heads, which happens with probability p log of 1 over this, 1 over q power n minus 1 p, which can be split into two sums, q power n minus 1 p log of 1 over q power n minus 1 plus summation q power n minus 1 p log of 1 over p. Summation is over n, so you can take the p outside and write it as q power n. Also, you can write q power n minus 1 as q power n over q, and 1 over q can be taken outside the summation, and this summation can be written as p over q times summation over all natural numbers q power n log of 1 over q power n. Plus p log of 1 over p summation q power n minus 1, n is over all natural numbers. Now the first term, again, log of 1 over q power n can be written as log of 1 over q whole power n, which is n times log of 1 over q, and then you can take the log of 1 over q outside. You can write this as p over q log of 1 over q summation n q power n, n is a natural number, plus p log of 1 over p, 1 over, you can take 1 over q common here too, q power n, n is a natural number. Then the formula summation n q power n over all natural numbers is nothing but q over or minus q whole square. So this is p over q times log of 1 over q times q over 1 minus q whole square plus P over Q log of over P. Another formula that they've given. This is a geometric series. Summation r power n is equal to 0 to infinity is 1 over 1 minus r. So here previously I had taken out this 1 over q outside, but I can actually keep it inside. Right, this is q power n minus 1 over all natural numbers. Or I could again change this to the sum q power n goes from 0 to infinity. So here um, n goes from 1 to infinity, but n minus 1 goes from 0 to infinity. In which case the summation of q power n is 1 over 1 minus q. So this would be 1 over 1 minus q. So you can cancel out the q and cancel out these two q's, and uh, p was actually equal to 1 minus q, so you can cancel out p and one of the 1 minus q's. So if you take out the 1 minus q common in both the terms, you'll be left with log 1 over q plus log 1 over p log 1 over p. So I made a small mistake in one of the steps. This was actually log of 1 over q power n minus 1, which means that this sum is actually n minus 1 times q power n So I'll keep the 1 over q inside the summation, and let me do this again. I'll only take out the p, write this as q power n minus 1 log of 1 over q. Log of 1 over q power n minus 1 is nothing but n minus 1 times log of 1 over q. So this is n minus 1, where n is a set of natural, n goes over the set of natural numbers. I take out the log of 1 over q. I'm left with summation n in capital N q power n minus 1 times n minus 1. Now here, since n ranges over all natural numbers, n minus 1 goes from 0 to infinity. So again, I can use the same formula with r is equal to q, and I will end up with p log of 1 over q times q over 1 minus q whole squared, which one of the 1 minus q gets cancelled because p is equal to 1 minus q. So now I am left with 1 over 1 minus q times q log of 1 over q plus p log of 1 over p. So 1 minus q is nothing but p. So you have a p in the denominator, and q log of 1 over q plus p log of 1 over p is nothing but the binary entropy function h of p. So if you have a biased coin which has a probability of turning up a heads equal to p, then the entropy of that source is h of p over p, where h of p is the binary entropy function. And you can check that this reduces to 2 bits when p is equal to half. That is, you have a fair coin, so h of half is 1, and then you will be left with h of x is equal to 1 over half, which is nothing but 2 bits. The question doesn't ask for a general formula, so if this comes up in an exam, you can just do it by taking p equals half, which is much simpler, as you can see. And the second part of the question, where you're asked to form a series of yes no questions to uh, find out which coin toss was the first heads, you could form the questions the following way. Question 1 is x equals 1, that is, did you get a head in the first toss? If no, then question 2 is if not, then question 2 is x equals 2. If not, you can ask the third question is x equals 3, and the average number of questions is summation p of n log, summation n times p of n times n, where n can be one question, two questions, three questions. So the number of questions you have to ask can be any natural number. And probability that n is 1 is, so you need to ask only one question: if the first head says a toss, if the second head, uh, if the first toss is a heads, and you need to ask two questions: if the second toss is a heads and the first toss is a tail, which occurs with probability half squared. You need to ask three questions: if the first two tosses were tails and the third toss is a head, which happens with probability half power 3, and so on. So P of n is half power n, and n ranges over all natural numbers. So this summation using the formulas that we saw earlier will be equal to 1 over half over 1 minus half whole squared, which is nothing but 1 over half, which is 2. So on average, you will need to ask two questions to find in which toss uh, the first heads occurred, which is also equal to the entropy. So entropy really is the number of yes no questions you can ask to find out the value of the random variable on average. That is the minimum expected number of questions you need to ask to find the actual value of a random variable when an experiment is carried out. Alright, we'll go to question number 2. The second question asks, um, it's on the entropy of functions instead of entropy of a random variable. So let x be a random variable taking on a finite number of values. X finite x is a random variable taking values in script x, where cardinality of script x is a finite natural number. What is the general inequality relationship of h of x and h of y? So the relationship between h of x and h of y, if the first question says y is 2 power x, then what is the relation between h of x and h of y? The second part asks what is the relation if y is cos x. So I'll do this for a general function. So I'll say y is g of x, where y can take values small y from script y. The probability that y takes a value small y is equal to a sum of probabilities p of x for all x such that y is equal to g of x. Now consider all x's that are mapped to the same y. That is, set of all x such that g of x equals y. Then let's call this script x dash or script xy. Then the summation of p of x log p of x for all x values in this set script xy is less than or equal to summation of p of x log p of y summed over all x in script x power y. That is because each of the p of x values is less than or equal to p of y. Suppose there is only one value of x that maps on to y, then p of y is equal to p of x. If there are more than one value x that map onto y, since the probabilities of each of those x's is non-negative, p of y, which is the sum of those probabilities, p of y is summation of p of x for all x such that y is equal to g of x. So p of y is actually greater than or equal to each of the individual terms in that sum, since all the terms in that sum are non-negative. That is, this is greater than or equal to p of x for each x. The sum of p of x over all x's that go to y is obviously greater than the sum of p of x for one of those x's, greater than or equal to. And the equal to comes if there is only one x which goes to y that has non-zero probability. If there are multiple x values that go to y with non-zero and such that those x values have non-zero probability of occurrence, then the equality is actually strictly, it's a strict equality. So p of x will be less than p of y. In any case, it's less than or equal to log p of x is less than or equal to log p of y. So summation of p of x log p of x will be less than or equal to summation of p of x log p of y. But log p of y is one particular number. The summation is over x's, not y's. So you can take out the p of y outside, log p of y outside. So this will be equal to summation. You take log p of y outside, log p of y, sum of p of x over all x in script x power y, and that sum is nothing but p of y. So log p of y times p of y. So you can do this for all values of x. Summation the entropy h of x is minus summation p of x log p of x over all x. You can split this sum into sum over all x such that g of x is y1 p of x log p of x plus minus summation over all x that go to the second value in script y p of x log p of x, etc. Or in a simpler form, you can write this as first you pick a value of y, then you sum over all those x's which go to that value of y, and the quantity you're summing is p of x log p of x. And this you do for each value of y in script y. Then you'll get h of x. And from the above inequality, this is greater than or equal to minus p of y log p of y summed over all y, which in turn is equal to h of y. So if y is a function of x, then the entropy of y is less than or equal to the entropy of x. H of x greater than or equal to h of y with equality if and only if g is 1 to 1 with probability 1. So what that means is, so what with probability 1 means is the following. So probability of the event that contains all outcomes in the sample space such that G is 1 to 1. this is equal to 1. In other words, for every outcome in the sample space with non-zero probability, G is 1 to 1. So suppose there are outcomes in the sample space that occur with that have zero probability of occurring, then we need not consider those outcomes. So we are only concerned with outcomes in the sample space that have a non-zero probability. For those outcomes, if the function g is 1 to 1, that is, the value of random variable x has a 1 to 1 correspondence with the values of random variable y, then we say g is 1 to 1 with probability 1, and only in that case h of x is equal to h of y. So basically what I mean to say is, in this summation, there is, in the summation, p of y equals summation of p of x such that y is equal to g of x. There is only one term which has non-zero probability, and if there, either there's only one term, or if there are more terms, there is only one term which has non-zero probability. That's the treatment for a general function. Now to come to the question that was asked, they didn't ask for a general question, a general function. A part A asked what is the relationship for the function y is equal to 2 power x. So this is a one-to-one function, exponential function. It would be something like this, right? This is y equals 2 power x. Which has a slope of log 2 base e at x equals 0 and passes through point 0 comma 1. So that's the function. Only thing is that the domain of the function is not, domain of y is equal to 2 power x is, the curve that I have drawn here is all real numbers, but the domain of this function is all the values that the random variable capital X can take. Uh, Even in that case, it's a one-to-one function. Therefore, h of x is equal to h of y. Since it's a one-to-one function, uh, if x takes the value x1 with probability p of x1, then y1, say it is equal to 2 power x1, has probability p of x1. So the probability distribution of y and x is the same, and since entropy is only a function of the probability distribution, they both have the same entropy. Y is equal to Cos x is not necessarily 1 to 1, depending on what values script x can take, what values script x has. Um, Cos of x can be many to 1 or 1 to 1. So the graph of y is equal to cos x would be something like this. It's periodic. So if x takes the value 0, that is if 0 belongs to script x and 2 pi belongs to script x, then y for both cases will be 1. So there are two values that are going to 1. So probability that y is equal to 1 would be equal to the sum of probability that x takes the value 0 plus the probability that x takes the value 2 pi. So p of y is greater than or equal to p of x in both cases, which would mean that h of y is actually less than h of x. But suppose x takes only values in uh, in this interval, then that is a one-to-one function, and h of x is equal to h of x. So we can't really tell unless we know what values x takes. Okay, that is it for question number 2. Next is question 3. This is on minimum entropy. The question is, what is the minimum value of h of p1, p2 up to pn, which is h of the vector p as vector p ranges over the set of n-dimensional probability vectors. Find all vector p's which achieve this minimum. So you have h of p1 to pn, which they write as h of vector p, where vector p is a n-dimensional vector. Vector p belongs to Rn, and summation of pii is equal to 1 to n is 1. Now our question is to find minimum of h of vector p over all vector p's. And also we have to find vector p's which achieve the minimum. So first note that pi is greater than or equal to 0, less than or equal to 1 for all I in this set n. So this is notation for the set 1, 2, 3 up to n, square bracket n. Now if pi equals 0 for some I, by definition pi log pi equals 0. If pi not equal to 0, then pi is less than or equal to 1, which implies 1 over pi is greater than or equal to 1, which implies since log is a monotonic increasing function, log of 1 over pi greater than or equal to log 1, which is equal to 0, and pi greater than or equal to 0. Therefore, pi log of 1 over pi is greater than or equal to 0. Pi log 1 over pi equals 0 if pi equals 0 or pi equals 1. We know that h of x greater than or equal to 0 for any random variable, that is h of vector p is greater than or equal to 0. Consider the distribution p pi equals 1 for some I and 0 for all other i's. Or a better way to say is that pi equals 1 for some I equals j and 0 for all I not equal to j, where j is some fixed number in the set 1 to n. That is, vector p is 0 in all places in the ith place or ith coordinate it is 1 and again 0 in all other places. And h of this vector p is that this vector p is valid because it's an n tuple and the sum of all its entries is 1 and the entropy of this is summation of pi log 1 over pi. I goes from 1 to n, which is summation 0 log 1 over 0 I not equal to j plus summation 1 log 1 over 1 where I is equal to j, which is nothing but 0 plus 0, which is 0. So h of vector p is lower bounded by 0, that is h of vector p is greater than or equal to 0, and we showed one particular vector for which h of vector p is equal to 0. So the minimum value is 0. And if h of vector p is 0, that means that pi log 1 over pi is 0 for all I, because pi log 1 over pi is greater than or equal to 0. So the sum of non-negative entries can be equal to 0 only if the entries are all 0, which means that the PIs are all zeros or ones. So if uh, and also the sum of all PIs is equal to 1. So there must be at least one PI which takes the value 1. But if there are more PIs which take value 1, the sum will be greater than 1. So there can be at most a single PI which takes the value 1. And since all the PIs must be 1 or 0, the rest of them must be 0. So these are the only vectors which have entropy 0. That is, they achieve the minimum entropy possible. So the answer to the question is minimum h of vector p is 0. All vectors vector p such that h of vector p equals 0 are of the form 1 0 0 etc., or 0 0 and the last entry is 1, or 0 1 in the middle in ith place. I goes from 2 to n minus 1, and the last entry is 0. Next question. Question 4. The entropy of functions of a random variable. Let x be a discrete random variable. Show that the entropy of a function of x is less than or equal to the entropy of x by justifying the following steps. X is a discrete random variable. G is a function of x, which implies g of x is also a discrete random variable. Show that h of g of x is less than or equal to h of x by justifying the following steps. So they actually give you the steps, you have to justify those steps. First, they start out with the joint entropy of x and g of x, which they write as h of x plus h of g of x given x. So, why is this true? The justification you have to give, and that's the justification for a. Then you can write this as h of x. That is, h of g of x given x is 0. What is the justification for that? That is b. Then you can also write h of x comma g of x as h of g of x plus h of x given g of x. The justification for that is c. Then you write this quantity is greater than or equal to h of g of x. And the justification for that is d. Thus, h of g of x, which is less than or equal to h of x comma g of x, but h of x comma g of x is equal to h of x. That h of g of x is less than or equal to h of x. So you have to give justification for each of the steps. The justification for A is chain rule for entropies. And the justification for C is also chain rule of entropies. So by chain rule, h of x comma g of x can be written as h of x plus h of g of x given x, or it can also be written as h of g of x plus h of x given g of x. That's the chain rule. Justification for B is h of g of x given x is equal to summation over all values that x can take, probability of x times h of g of x given capital X is equal to x. For a particular value of x, g of x is fixed because it's a function. So for each value in the domain, there is only one value in the range. So for each value that capital X takes, there is one particular value that g of capital X takes. And that means there is no uncertainty in the value of g of capital X. If you know the value of capital X, you know that the random variable X has taken a particular value, then you also know that g of x has taken the value g of small x. So there's no uncertainty in what value g of x, capital X, can take. So this is 0. This is true for all values small x. Therefore, h of g of x, comma g of x given capital X is summation over all x p of x times 0, which is 0. That's the justification for B. So B was you said this is 0 and dropped it. So h of x comma g of x is equal to h of x. Then part D says h of g of x plus h of x given g of x is greater than or equal to h of g of x. So that means this is greater than or equal to 0. That's what you have to justify. So the justification h of x given g of x is greater than or equal to 0. We know that entropy of any random variable is non-negative, and with equality, if and only if x is a function of g of x. That is, g is 1 to 1. So more precisely, if x is a function of g of x and g of x is a function of x, then uh, g is a bijective function. Um, so uh, X is a function of g of x. Let's say that function is f. So x is equal to f of g of x, which would imply that f and g are inverses of each other. So, but when we say g of capital X, the codomain is simply the range. So when we don't specify the codomain, it's just taken as the range. So it's an onto function also, just by convention. That is all values g of x is considered as the codomain for the function g. I guess that's taken care of if g is 1 to 1 and x is a function of g. X is a function of g of x. Okay, so those are the justifications for each of the steps, and from that we can get h of x comma g of x. H of x is greater than or equal to h of g of x. So question number two also dealt with the same thing for particular functions, but we proved it for general function y is equal to g of x. But we proved it by using the definition of entropy and a little bit of algebraic manipulation. Here we prove the same thing using the properties of entropy, such as the chain rule and that conditioning reduces entropy, etc. Next, we go to question 5. Show that if h of y given x is 0, then y is a function of x. That is, for all x with p of x greater than 0, there is only one possible value of y with p of x comma y greater than 0. The solution So the proof of this is as follows. Proof by contradiction. Assume that for the purposes of contradiction, there are two values of y1 and y2 such that p of x comma y1, p of x0 comma y1 greater than 0, p of x0 comma y2 greater than 0 for some x0. Because the statement says for all x with p of x greater than 0, there is only one possible value of y with p of x y greater than 0. And we are saying that there is at least one value x0 such that there are two possible values y1, y2 such that p of x0 y1 is greater than 0 and p of x0 y2 is greater than 0. Now p of x0 is summation of p of x0 comma y over all y which is greater than equal to p of x0 comma y1 plus p of x0 comma y2. But each of these p of x0 comma y1, p of x0 comma y2 is greater than 0, so this is greater than 0. Therefore p of x0 greater than 0. Then p of y1 given x0 which is equal to p of y1 comma x0 by p of x0 is greater than 0 because p of x0 comma y1 is non-zero, p of x0 is also non-zero. Similarly, p of y2 given x0 is greater than 0. Also, p of y1 given x0 is less than 1 because if p of y1 given x0 equals 1, then p of y1 comma x0 is equal to p of x0, but p of y2 comma x0 greater than 0, therefore p of y1 comma x0 plus p of y2 comma x0 is greater than p of x0, but p of x0 is greater than or equal to p of x y1 comma x0 plus p of y2 comma x0, which is a constant contradiction. You're saying p of x0 is greater than p of x0. So therefore P of y1 given x0 less than 1 and P of y2 given x0 is less than 1, which implies log 1 over P of y1 given x0 is greater than log 1, since log is monotonically increasing, which is 0. So log of 1 over P of y1 given x0 is greater than 0, and log of 1 over P of y2 given x0 is greater than 0. Now h of y given x is equal to summation p of x over all x, summation over all y, p of y given x, log 1 over p of y given x, which is greater than equal to, since the sum is over all x, if you drop all the x's other than x0, then that sum is greater than one individual term. Similarly, if we, instead of summing over all y, if we sum over only two particular values of y, then the summation is actually greater than or equal to. So this is greater than or equal to p of x0 times p of y1 given x0 log of p of y1 given x0 plus p of y2 given x0 log of 1 over p of y2 given x0, which is actually greater than 0, because each of the terms p of x0, p of y1 given x0 log of p1 over p1 y1 given x0, p of y2 given x0 and log of 1 over p of y2 given x0, each of those is greater than 0. So the sum of products of those terms will also be greater than 0, which is a contradiction because it was given that h of y given x is equal to 0. But this says h of y given x is greater than 0. So it's not possible for any x to be assigned to two different values of y. That is, there can't exist two values y1, y2 such that p of x given y1 greater than 0 and p of x given y2 greater than 0. Also, for all x with, the statement says for all x with p of x greater than 0, there is only one possible value of y with p of x comma y greater than 0. But clearly we can see that if p of x comma y greater than 0 for any values of x and y, then p of x must be greater than 0. So it's just not possible for p of x to be equal to 0 and p of xy to be greater than 0 for some value of y. So if p of x is 0, then p of x0 is equal to 0 for some value of x, then p of x0 comma y is also equal to 0 for all values of y. So if some x has priority p of x equals 0, then no matter which value of y you assign it to, you can assign it to multiple values of y, but the probability of x comma y will be 0 for all those. So there is no possible value of y for which p of x comma y is greater than 0. So it doesn't really matter to us what zero probability values get mapped onto. So those are some problems based on the basics of entropy. These problems are based on properties that we studied at the very beginning of the chapter. So I'll be recording a few more of these problem solving videos of much more complicated problems also, and I'll try to solve as many of the text problems as possible. So that's it for lecture 7. I'll see you in lecture 8.